Melvin asked that maybe we ask if you have any specific questions, and then there's one topic called sulfates. And I'm not going to go into this in great detail, but if you have any specific questions on that, I can kind of talk a little bit through it, and if we can address specific questions if you have any. So is this something you have interest in or not?
Yes.
Yeah, probably so. I kind of figured that. Well, to give you a little history, I recently spent a little bit of time talking to Jim Mitchell, who's he was, of course, John knows him well, but he was a National Academy professor at, or still is, at Berkeley. And Jim's a geotechnical expert. He also has a wonderful textbook on fundamentals of soils that I use in the pavement, or in a course that I teach on chemical stabilization of soils using polymers and other traditional stabilizers and non-traditional stabilizers. We go through the whole gamut of stabilizers. But had a chance to speak with him recently, and I remember first time I was really intrigued by the sulfate issues was back when he gave his Terzaghi lecture back in 1985, 86, I think it was. And he talked about some surprising things that happen in soils, and one of them was the Stewart Avenue case, which was in Las Vegas. So Stewart Avenue was an avenue that was treated there with quicklime, and the quicklime stabilized the soil pretty well. And of course that's a very arid area, as you know, and a dry climate. And the lime was not mixed very well into the soil, as I recall, in some areas. And they had some torrential rainfall events, or had a big rainfall event. And some of the areas where it wasn't mixed very well, the rain got to the quicklime and hydrated it. So what happens when you hydrate the quicklime is you you get that high pH. And when you get the high pH, it reacts with the soil constituents to form a pozzolanic reaction. Well, one of the things that happens in the presence of soil minerals, clay soil minerals, lime and sulfates, is that you can form a mineral such as ettringite, which is a calcium aluminate sulfate hydrate. So the sulfate interrupts that pozzolanic reaction, so to speak, in favor of the formation of this mineral called ettringite, which can be very expansive. If you form ettringite in a closed container where you have all the water present that you need, it's not going to expand. It'll actually contract a little bit because the molar volume of the mineral is actually a little bit less than the molar volume of all the constituents that you put in there if you have the right recipe. But if you have water coming in from the outside, that water that's available from the outside is going to make sure that when the ettringite forms, that you're going to have a considerable expansion. And that's where water is coming from. You don't always, the water is going to get there from the outside. And when you do that, the ettringite mineral holds so much water that it results in a very large expansion. So, Jim Mitchell's paper, for the first time, identified the basic mechanism, and then since then, we've done some work on that, and others have done some good work as well. But Dr. Papalat here at UT Arlington has done some really good work, and his people, and we've done some. We're doing some work together now, talking together on doing some things there. But what's really interesting is there are several ways to attack it. One way is to look at some stability models of when it's stable and when it's not stable, and what you could do to prevent the formation, and also the kinetics of the formation, and so forth. To make a long story shorter, we looked at Etrangite as a potential problem when the Denver airport was done. And of course that was back in the mid-'80s to early '90s when we were looking at the Etrangite problems out there, and we sort of came up with a hypothesis that, this is 25 years ago, whatever it was, we came up with a hypothesis that, well, if you could add as much water as you could to solubilize the sulfates and extend the mellowing period, then perhaps you could form this Etrangite when the soil was in its uncompacted state, and if you could form this mineral then, it wouldn't, once you compacted it, you'd kind of get away with it. You wouldn't expand after it's already been compacted and cause all that distress. And we really didn't think too much. We didn't, being civil engineers and not chemists, we thought we knew a little bit of chemistry, but we had a lot to learn. And obviously the solubility of gypsum, if gypsum is the source of sulfates, is quite low, and it takes an awful lot of water to solubilize even something like 0.3%, which is kind of a threshold level that we've come up with. And you couldn't never add enough water practically to solubilize that level of sulfates and cause it to form all the Etrangite that it's going to form. But we kind of backed into something, because what happens is we found out is that even though that's true, if you add as much water as you possibly can, you start to nucleate some of the crystals of Etrangite. And like any crystal formation, there's the nucleation phase, and then there's the sigmoidal development of the crystal structure. But you don't develop that crystal until you actually nucleate the crystal site. So by adding as much water as you can, and by having a level of sulfates that is not going to produce too much Etrangite, you're on the right track. And that's what we did at the Denver airport. We said that we know that from practical experience that if you have less than about 0.3%, which is about 3,000 parts per million, that you're not going to get excessive expansion. And that is assuming that you don't allow sulfates to enter from outside that area. And so then we said, okay, if you add as much water as you can, and you extend the mellowing period, then perhaps you can form this Etrangite before it's a problem, before it's compacted. So, like I said, although you can't solubilize all the sulfates if they are in the form of gypsum. Now, if it's a sodium sulfate, you can, because it's much more soluble. But if it's gypsum, which it almost always is, you can't. But you start to nucleate these crystals. And you start to nucleate these crystals by adding as much water as you can and by mixing it as intimately as you can. So we actually backed into something that worked pretty well out in the Denver airport area. And we extended the mellowing period because the C.T.L. Thompson, who was doing the work out there, was very aggressive in trying to understand this process and keep it from happening. So we used about 3 to 5% above optimum mixing moisture, and we mixed it very, very intimately. So you spread out these little nuclei that were well distributed, and we extended the mellowing period to somewhere between 4 to 7 days, typically about a week. Now, people don't want to do that, but we did it there, and we were able to get away with stabilizing soils with up to almost 1%, in some cases, sulfates. And remember, what's happening is that we're adding enough water to trigger nucleation sites, we're mixing it intimately, and we're distributing it uniformly So some of the etrangite is going to grow in void structures, not going to be confined into a concentrated area. And the soil can pretty much accommodate that. And then you're extending the mellowing period, so before compaction, you're starting to trigger these nucleation sites in well-distributed regions. So that is something that was then adopted over a period of time by TxDOT, in which we said that somewhere between 0 and 0.3% or 3,000 parts per million, add as much water as you can, extend the mellowing period as long as you can, and you're pretty safe, as long as you don't keep sulfates from moving in from outside. And sulfate's a very mobile ion and can move long distances if you don't keep it controlled, keep drainage controlled. Then if you get sulfate contents above about 3,000 parts per million to about 5,000, your risk increases, but you can still get away with it if you're careful. And then if you go above about 5,000 parts per million, you really have to take some extra steps of care. So that is what the basis of the TxDOT approach has been, and other approaches. And I also wrote a preferred practice for NCHRP in 2007, where we talked about how to stabilize soils in general, but that was web document 145, NCHRP 144, and then NCHRP web document 145 was how to stabilize high sulfate soils, preferred practice. And it talks about all these approaches. So that's something that you could look at. As a matter of fact, I got a slide at the end of this that reminds you of that, and it's in your book on those documents, so you can go back and take a look at those. But that's kind of the sort of the history of how we got there. And then there's an ASCE geotechnical journal paper that was published, I think it was 2009, 2010, that sort of summarizes the basis behind this approach. Later on, we have, over the years, we've been continuing to work in using stability models to evaluate why sulfates occur, why etrangite occurs, how you can control it. And one of the ways that we've determined that you can prevent it from happening, or at least form another mineral that's going to be stable rather than etrangite under those conditions, is to add soluble silica. A source of soluble silica helps you form another mineral in place of etrangite that's typically not expansive. And we actually thought that was the case way back 20-something years ago from experience, but now we have proof that that's the case through using these stability models. That's why sometimes a good source of granulated blast furnace slag or fly ash or something of that nature with a good source of soluble silica can prevent the formation of etrangite under certain conditions. So soluble silica is a valid approach to helping to prevent etrangite formation from occurring. So I guess that is kind of a historical background without going through all the slides to show you. So we've looked at it from a couple of different approaches. One is to say, well, first of all, you want to try to form it early. And although you can't add enough water to completely solubilize all the etrangite, you can at least get it started by forming nucleation sites, and then you can mix it as intimately as possible to distribute it as uniformly as possible and extend the mellowing period as long as possible, and you have your best chance. On top of that, we know that both from stability models and from practical experience, from empirical experience, that if you're less than about 3,000 parts per million, you're safe for a number of reasons. And then if you move up the scale between 3 and 5 tenths of a percent, you have higher risk. If you go above about 5 tenths, your risk is considerably higher. But those are valid approaches that we have based upon good field experience as well as some good fundamental principles. The other thing to pay attention with there is that once you have established the fact that you have controlled the amount of sulfates that you have, and you take the precautionary steps to add as much water and to mix it as intimately as possible and to extend the mellowing period, you want to make sure that you have proper drainage control so that you don't get sulfates coming from the side or from below. There are two cases which I've seen historically, one where I was working as a consultant, one was a Berthoud bypass in Colorado, which was a concrete pavement. And the concrete pavement blew up. This was a number of years ago, about 15 or so years ago, maybe 20. And we went out there and we took a look at what was going on. They brought in a material that was carefully controlled. They took thousands of sulfate tests, and the material that was stabilized with lime was low in sulfates. But when you went down there, if you go out there, if you went out there, if you had gone out there, and you looked at the pavement, or you looked at the soil below where this fill material was brought in, you could see the sulfates, the gypsum crystals in the soil below. And of course what was happening is you would get this capillary rise where the sulfates were migrating into the lime stabilized fill material that came in, and the expansion occurred. And then another source was in Brody Lane in Austin, Texas, where the sulfate content of the soil in the subgrade was relatively low, and this was about 20-something years ago. But you had these embankments, and the embankments along the side, the pavement was sort of, depression, and you had these embankments, natural embankments, they weren't embankments, it was a cut down into this region, and these cuts were laden with sulfates. So when the water drained down and pooled in the subgrade, it brought all these mobile sulfates into that region, and of course those mobile sulfates were the source of the expansion. So both of those demonstrate that you've got to control moisture movement, which can bring sulfates with it. Because unlike something like calcium, which is a very active ion and will react, sulfates can move a long distance before they begin to react. So they tend to be a very mobile ion. So, those are the basic principles that I think we have to be concerned with. So let's just go over those one more time. One is we actually have a really good handle from basic equilibrium models as well as empirical experience that we know what levels of sulfate contents are problematic. Anything below about 3,000 parts per million, as long as you don't allow sulfates from outside to come in, is a good, safe level. If you move between 3,000 and 5,000, you're still pretty safe, but your risk goes up. If you're greater than 5,000 parts per million, then you really want to be careful and study the problem extensively. But you can even go higher than that if you're willing to take extreme steps. And one of those may be to add some type of an additive to it to help prevent the sulfate, or to help prevent etrangite from being the stable mineral that develops. So, the quantity of sulfates is the obvious one. The second one, of course, item that we need to be concerned about is, like I said, to add as much water as we can and to extend the mellowing period as we can, as long as we can, so that we can trigger the nucleation sites and we can distribute them as uniformly as possible and allow those nucleation sites to take root before we compact it. And that gives us the best chance of getting an even distribution so that the sulfates can grow in the voids and not be concentrated into an area that's going to cause a heave to develop. And of course, that's coupled with a reasonable quantity of sulfate. And then the third thing is to make sure that our drainage is controlled so that we don't get migration of sulfates either laterally or from capillary rise into the lime-treated layer. And as long as you do those, you have by far your best chance. And then finally, I guess, if you are dealing with some sulfates, and you take these precautionary steps, and you want to do one other thing that can help you guard against sulfates, is you can, and this requires probably that you deal with somebody with some expertise in this area, maybe to add some type of a additive that is going to reduce the potential for the formation of etrangite, such as adding a source of soluble silica that will normally, or in many cases, trigger the formation of a mineral that has a greater equilibrium potential than the formation of etrangite in that particular environment. So that's kind of a history. I've got a whole bunch of slides, but it would take a while to go through those, so I thought that might be the best way to approach this, was kind of talk our way through it. And if you have any questions, I'd be happy to answer your questions. Yes, sir?
What is the source of soluble silica?
Well, a source of soluble silica, one is a fly ash, because, of course, fly ash is the material that is the residual material from burning of coal that does not combust, and it is normally comprises silica and alumina, because those are the most plentiful some of the most plentiful elements there in the Earth's crust. And so when it melts in the stack, it's forming, when it vitrifies, it's forming a soluble form of the silica and the alumina. And the problem with, well, if you form, not all fly ashes are equal, but some fly ashes are a real good source of soluble silica. And even though they provide other compounds as well, they seem to work quite well. And another good source of soluble silica would be ground granulated blast furnace slag. And then another would be ricol ash, and then there are things like other sources of silica as well. But they should be an amorphous form of silica, something that would be reactive. Other questions? Yes?
Would you define